Thank you, Carmen. And it is a great pleasure to be here. I'm mainly going to talk to you about a review that we did recently for the annual reviews of marine sciences. And this is the title. I think the title I gave you included the word global in between here. These are my co-authors, a very smart postdoc from France that works with me, and Tim Pennington, who's worked with me for many years. I've been supported, of course, by many people, Gernot Friedrich, Reiko Michisaki, Marguerite Blum, and Chris Wall. I was recently at a NASA meeting before I came here, and I picked up this animation, and the caption that I put on it was "the world as an ecological unit." What we have here are images of chlorophyll from the ocean and NDVI on land, both captured by CWIFs, the little satellite that performed so well for so many years that it unfortunately is now no longer operational. And this image brought to mind to me the fact that that indeed the world is sort of an entity in itself, and we need to start treating it as an entire ecological unit. And of course it is interesting, and as we describe in the paper, that primary production in the oceans is equivalent to that on land, and of course it's carried out by very different organisms. Most of the photosynthesis on land is carried out by organisms that are about our same scale, while those in the ocean are organisms that we have to use microscopes to look at. This morning I was looking at the animation. There's lots of interesting things here, and one of them is what seems to be an out-of-phase relationship between land and terrestrial systems. I won't get into that today. What I wanted to do first was to start by introducing the place that I work. I work at the Monterey Bay Aquarium Research Institute. It's in a small fishing town in central California, in Moss Landing. My office is right here. I have a horrible view. It was founded by a philanthropist by the name of David Packard, who, with his partner Bill Hewlett, formed Hewlett-Packard in 1939. Mr. Packard had two daughters who were interested in marine biology, fortunately for me, and they convinced him to build the Monterey Bay Aquarium in early 1980s. It was such a success that they were making money, so much money that they didn't know what to do with it, and the daughters talked to their father about investing it in research, and he said, "No, you keep those that and reinvest it in the aquarium itself. I will start the Monterey Bay Aquarium Research Institute." Mr. Packard gave us this mission. I won't read it to you. I just want to mention that my PhD director, Dr. Richard Barber, was the first director of that institute. He brought me with him and then proceeded to return to Duke. I stayed behind. We've had a series of very distinguished directors. The most recent is Chris Scholin, who's a pioneer in genetic analysis in situ, and was my first postdoc while at Imbari. I always tell this joke, you should be nice to your students and your postdocs because you never know when they could become your boss. So Fizz, be nice to. We have several themes. We're all involved in almost all of them, but those that I am particularly related to are ecosystem dynamics and ocean biogeochemistry, which we have often treated separately. And as we go to look at things in the future, I think we need to bring them closer together. We have ships. These two will be soon replaced by a single vessel. We have ROVs and AUVs. This one is the most exciting one that is just recently been developed by Jim Bellingham and his engineering group. The first one was named Tethys. It's called the long-range AUV, and it's somewhere in between these larger vehicles and these gliders that are capable of running for significant periods. It can carry much more payload than a glider, and it can operate much faster as well. And it just is in the process of completing its first long-range mission. It came out here to approximately 500 nautical miles from shore, rendezvoused with the ship here around a drifter, and then came back in and rendezvoused again with the drifter. And this is the drifter track that just happened about a week ago. I could follow this now remotely from my computer, the wonders of the internet. And here is the AUV circling around the drifter, making a variety of biogeochemical measurements. And all of this capability was actually being controlled from shore, not from the ship itself. The ship was just there just in case they needed to recover their vehicle. We develop instruments. Colleague Ken Johnson has been a pioneer in putting nitrate and soon pH on many Argo floats. And we've been doing a little pH work on our own, mostly near surface. We have been developing some very inexpensive systems for tidal deployments and also some for very near surface moorings. As we know, one of our greatest problems in the ocean is biofouling, and we have been using these copper covers for them. This effort is part of a multi-institutional project where we have picked in 4 different areas, an area that is strongly influenced by upwelling and one that isn't in each of these areas. And we've deployed small moorings where we have a variety of instrumentation, and also deployed these instruments in the intertidal. And physiologists are interested in trying to understand the impacts of ocean acidification on mussels and urchins. And this is our first data set, and again, I'm not going to spend any time on this, just to show that we are actually able to collect a pH and temperature data from these loggers in the intertidal on this mooring surface, and then in that same mooring at depth at 20 meters. So now we get to what my interests have been at MBARI, which is the collection of these long time series. I've spent almost my entire career, which is sometimes a bit depressing, collecting time series that are only 20 years long. And of course, the problems that we're facing are problems that are much longer scale than these. I'll come back to this same slide, so I'm not going to go into it in a lot of detail. But we did start this time series as soon as we arrived in Monterey, or soon after, in around 1989, and now has over 20 years. And I think that's all I want to say on this right now. And as I said, I'll come back to that. We started our series of CO2 and pH a little later than that. And even in this very noisy environment, we're able to pick up these trends over time. And of course, when I started my PhD dissertation, there was a lot of things that weren't around. One of them was this worry about the future. We were just starting to think about it. But today, these problems are in our face, and it's up to the students of today to grapple with them. On the top is the average temperature anomaly for the ocean, sea level from San Francisco Bay. Here's our time series of pH and PCO2, and then this variability in the abundance of certain pelagic species, the anchovy that collapsed off Peru in the early 70s and was replaced by sardines, and then has returned recently as the sardines had disappeared. So we have these time series with different trends in them, but these trends, as we can see, are not uniform. There was a period of actually cooling in the early 1900s, and then a period of what appears to be a fairly rapid warming, and then a period where there is not much change whatsoever, and then there's a period again of rapid warming, which we are concerned about and think is associated with changes that we are making. And there may be an indication of another change in trend up here, and I'll argue that maybe that is a real change, and we'll have to wait and see what happens in the future. You see the same types of changes in the sea level record, and in fact in the sea level record in California, there's a slight decrease in this trend, and that's one of the topics I will be talking about. So the outline, I'll very quickly try to go through some of the things that we're doing at the Monterey Bay Time Series, and then look at global climate variability as it occurred during the 20th century. We'll look again fairly briefly at a number of time series of primary production, including one locally. And it was actually at the symposium in honor of Dr. Fraga, who's present here, that I really started to put together the stories that are told in this annual review paper, and in fact met some of your colleagues who provided the information for that time series. I'll look into the past to see if we can learn something about what might be coming in the future. I'll throw in a few other vignettes here and there, and if we have time, and we probably won't because I think I have too many things, I'll say something about not your future, but my future. So we started in '89. We have combined a wide variety of tools, as everybody does. We have published a number of papers. And more importantly, I think these time series help to generate ideas and process studies, because as you notice things, you start thinking about, oh, I don't know what's going on here. How do I explain that? And we need to develop process studies then that look at those processes that we found in these time series. For us, it's very important because of our strong technology focus. It provides us with this natural laboratory, and it's so close that we can do these things rather easily. And of course, what I have always been interested in is I wanted to understand how biology responded to climate variability and now to global change. These are some of the pictures from the first figures of the paper, and I'll just go through them in general terms. We're now, again, so lucky to have these wonderful satellites available to us that were not available to me when I was working as a student, but now can provide us with these wonderful pictures of the general character of the ocean. The top one is dynamic topography as gotten from sea level, and the places where these contours are close together is places where the currents are very fast. And the Kuroshio is described here, as is the Gulf Stream. And then in our parts of the world, our currents are fairly slow and broad. The California current technically extends from here all the way across here because most of the flow is in this direction. And most, of course, this flow is driven by the winds. And the winds here are presented in a couple of different ways. The colors represent the maximum wind speed. And then, because the wind, of course, is a vector, when you average that vector, what shows up is that, while the strongest winds are always at the higher latitudes, the steadier winds are in the mid-latitudes. And these steady winds, of course, we all know as the trade winds that drive the upwelling along our coasts here. This circulation leaves an imprint on the chemistry, and this is the depth of the nutricline as estimated from the World Ocean Atlas data set. Again, a resource that wasn't available to me when I was young. And the way that is calculated is we take the World Ocean Atlas and calculate the depth, the depth to which there is a difference in 1 micromole. So where it's shallow, the change in nutricline, in nutrients, is fairly quick. While in these gyres, it takes you up to 150 meters or more to reach a change in 1 micromole between the surface and that particular depth. And of course, that is covered in primary productivity or is represented in that property as shown here. And these are the 5 sites that we looked at as part of this paper. Of course, the one that I was associated with, the US, starting with Jagoff, supported the Hawaiian Ocean Time Series and the Bermuda Atlantic Time Series. I was born just close to here, as Carmen said, so I have continued to work with my Peruvian colleagues who have assembled a very nice data set. And again, I was fortunate to meet people when I came here to Vigo last and got this data set. Here we are. Here's San Francisco Bay. Here's Monterey Bay. That cruise that I showed you, the AUV was going along, is along something we call line 67, and Carmen has worked on this data set as well. And of course, there is a lot of mesoscale variability. Although once you look at this mesoscale variability long enough, like some of us had, you find a lot that it's not as chaotic as you once thought it was. There is structure in chaos, or at least in the coastal upwelling system. If you deploy a drifter, surface drifter, it gets carried offshore and then gets caught in the California current as it goes poleward. If you deploy a float at depth, it gets trapped inshore and flows against the wind. In fact, most of the flow in these upwelling systems is counter to the wind in response to pressure gradients. These are the stations that we occupy routinely: Station C1, Station M1, and Station M2, and we have moorings at these locations. This is a temperature and chlorophyll. I'm going to pass on that. If we go along line 67, this is what the density structure looks like. And there are 3 domains that we describe. The upwelling domain, which in this case, this is about 0 to 500 kilometers. The upwelling domain occurs in a very narrow range of 0 to 30 kilometers or so. We then describe this other piece of enhanced nutrients and biomass and cooler temperatures and higher densities as the coastal transition zone, and then we finally get into the California current. What's always puzzled me and seems to puzzle the models is why the vertical structure is elevated so far offshore, because upwelling is really restricted to a very narrow range. And I believe it's somehow associated with the undercurrent dynamics that expand this 30-kilometer domain to almost 150 or so kilometers. It's interesting to look at the history of measurements because it tells you something about the history of the organizations that collected them. There was, at the beginning of the sardine fishery in Monterey, there was an effort that was started at Hopkins by a fellow by the name of Scosberg. And so we have a few measurements of temperature in Monterey Bay in the early 1930s. When the sardine collapsed, we started the Cal Coffee program. It's interesting that while the sardine was plentiful, there was no measurements made in the area. And then that carried on until the sardine never returned, and they started to run out of money. Mbari was established right around here. These are some measurements made by Moss Lang Marine Laboratories, and we have managed to fill that record in as well. And there are some interesting differences in the seasonal cycles here, but I won't get into those today. Just briefly, an introduction to anomalies. We make lots of measurements, and from them we create a smooth time series, and then we can average those, and then the average year looks something like this in temperature and something like this in chlorophyll, very nicely tied to the seasonal cycle of upwelling and light. And then we can remove that seasonal cycle from what we observe for a particular year, and we reach an anomaly field, which is something that we rarely have been able to do with biology or chemistry. We have these measurements that we make for moorings, and all I want to show you here is that we can now make these measurements of nitrate from moorings continuously, and we wanted to know how well our ship time series represented the data that's collected every 10 minutes or so. And we were able to convince ourselves that the blue line, which is our ship collected time series, represents the very high frequency variability rather well. So we feel comfortable that our anomalies well represent those from a year-to-year variability. Our area is dominated primarily by diatoms, like it is in almost any other coastal upwelling system. Here's a little conceptual model of what's happening in our upwelling system. Water with high nutrients and CO2 comes to the surface. A phytoplankton growth is stimulated. Most of the nitrate uptake is occurring here close to shore, but that phytoplankton growth or particles are distributed over a much larger area. Here's the area of high fluxes coming out, and then low fluxes offshore, so that the net flux of CO2 in this system tends to be close to zero. Something that's coming up more and more, and it was actually presented recently at the same NASA meeting by Greg Mitchell, who was confused by the relation he was finding between the E ratio and primary production. If some of you remember old papers like those in 1979, which was the Epley and Peterson paper, the Epley and Peterson paper described an F ratio pattern that looked like this. So that the higher the production, the higher the consumption of nitrate. But what we seem to find these days in many places is that the proportion of flux to the seafloor is actually higher at lower levels of productivity. And that's because there's a time and space discontinuity between the time you take up nitrate, the phytoplankton take up nitrate, and the place where that nitrate is exported vertically. Here are just some time series of CO2 from our local area, and I've compared those to that in the atmosphere close to us, and our patterns near shore are very similar. And this is actually exactly the opposite of what happens offshore, where physics tends to dominate. But in the coastal environment, biology does. So I've spent a lot of time, perhaps too much time, describing our time series. I want to now start going into some of these longer time scale changes that we tried to explain, that we observed locally and now try to explain globally. Here is our temperature, our time series of temperature, and if I showed you at the beginning and I extended further out, it's been cooler than normal after the 97-98 El Nino, which shows here. And nitrate has been higher than normal subsurface, and chlorophyll has been higher than normal subsurface, or at the surface as well. So something different here than it happened here. And in between, we had an unusual period of stratification, which occurred under these shallow nutricline conditions and led to a proliferation of dinoflagellates. And when this first happened, I thought, oh, maybe we're going into something different that I was calling the age of the dinoflagellates. Since then, the dinoflagellates have gone down. These dinoflagellates actually are interesting because they migrate vertically, and we have seen them do that with our AUVs to depth where they take up nitrate and come back up to the surface and photosynthesize. And in fact, they're able to lower CO2 below levels that we thought couldn't be reached based on the available nitrate that was originally in that time series. And I think this is still a possibility for the future, because history tells us that when the world was a lot warmer, these organisms were dominant along all of our coasts. Okay, another message for those of us collecting time series is that the length of record is important. And there's still a lot of debate about what is happening to primary production in the world. Is it increasing or decreasing? Unfortunately, even after all these years, we don't even know what the sign is. We don't know if the sign is increasing or decreasing. There was a paper published in Nature last year that suggested that the world's primary production is decreasing at a rate of 1% per year. I think that's actually wrong. I think they even got the sign wrong. I think primary production, at least over the last 20 years, has been increasing, and we'll see who's right or wrong about that. This was a paper published by Barenfeld et al. In Nature, and they were claiming that this decrease, one of the things they were claiming was this decrease was a result of some climate impact, warming. As water stratified, the trend in the ocean productivity was decreasing. Here I took the same data that they used and I plotted it with our Monterey Bay time series. And the other thing I will argue soon is that Monterey Bay is a place where I can predict what the change in world primary production is going to be. And the reason being is that the same processes that drive productivity in Monterey Bay are driving productivity globally. And we'll see if you believe me or not. And that's why these series are somewhat similar. And then if you extend that time series back in time, because our CWIFs started right here, and so their record they were working was this one. But if you extended that backwards, then instead of seeing a general decline in productivity, you see an increase. Now, one might argue that if you go back longer in time here, you might see something else. But the point is that when you're looking at a record, you need to understand where you are in this whole cycle, this world cycle. So this change that I'm going to get into here is happened over a variety of properties. We went from more to less small plants, and it was occurring in a number of places along the coast, in Monterey Bay in Southern California, in Peru, and in San Francisco Bay, interestingly enough. And in fact, there's some very nice papers by a person by the name of Jim Clorn that describe some of the variability in San Francisco Bay very nicely. So quickly now, we'll start to look globally to see what we can find that might help us explain these changes that we're seeing locally. We'll look primarily at sea surface temperature, and then I'll show you that for the recent record, these satellite time series show us that there is extremely strong coherence between the physical and biological properties. There are 4 modes of variability that are described with this analysis of statistical analysis, and I won't get into the EOF analysis, but needless to say, there are pros and cons to that. These 3 modes are Pacific modes, essentially, and this one, the M2 mode, is the Atlantic, the only Atlantic-dominated mode, and it's dominated by this, or it's called, has been named the Atlantic multi-decadal oscillation. What we've done here is we've taken the principal component time series for each of the modes, and then we've matched them with the regional mode that best represents them. And in this case, mode 1 is best represented by the El Nino index. The M2 mode is best represented here in yellow by the AMO. The M3 mode is best represented by the Pacific decadal oscillation. The M4 mode is best represented by the El Nino Modoki index and the North Pacific gyre oscillation. El Nino Modoki in Japanese is the same, is like, but not the same. So it was described by some Japanese scientists, and there is a fair amount of debate if this is really different from El Nino, or is it just a different stage of El Nino, or that El Ninos develop differently. But the interesting aspect of this mode, and it affects the Atlantic as well, is that its variability is increasing recently. And it's been talked about a lot as a big driver of what's happening along the California coast recently. But it is is this how global warming is going to be represented? Who knows? The other thing to note is that all of these modes have a big change around 2000. Is that just pure coincidence, or is there something bigger happening? I'm saying there's something bigger happening, but the record is too short for me to say that with certainty. So over the past century, M1, El Nino still is the dominant mode. It has a lot of interannual energy and some multi-decadal. M3 is like but not the same as the PDO, and the PDO is this combination of the M3 mode and the multi-decadal energy associated with M1. And then M4 is the combination of these, and you can perhaps separate them into 2 separate modes. If we remove the lower frequency variability from the analysis, then this is the first mode of decadal variability. And remember I told you that, and some of my colleagues get upset at me when I say this, that I can tell you what's happening in the world by just looking at what's happening in Monterey Bay. And that's because this triangle here seems to be the triangle that determines most of the variability in global primary production. So I'm not saying that the Atlantic is not important, but what I'm saying is this is the most variable area, and when you look at the variability in the record, it's driven primarily by what's happening here. And that same variability is being felt in Monterey Bay. There are 4 major changes in this record. One that happens in 1925. Maybe that was the beginning of the sardine. The sardine demise occurs right around here. There's a famous, at least for the Pacific, 76 regime shift. And then there's this recent cooling that I'm arguing perhaps is bigger than something that we've seen before. And if we look at the trends recently, if we just take the record from 81 to 2009, then this pattern of variability is well represented in this trend in SST. So this cooling that we're seeing over the last 30 years is driving, I argue, an increase in productivity in the world as a result of being in a certain phase. And below here, I've just plotted the M1, M3, and M4 modes, and you can see that prior to that, they're not in phase with each other, but after that, they all seem to be following this same phase. And this here was the period of the age of the dinoflagellates, and things have actually cooled even more here recently. As I mentioned before, if we take the different properties and we look at the first modes, this is SST. I've inverted this to show the cold phase. Sea level pressure. This is the southern oscillation pattern that drives the El Nino variability. Sea level. If I would have shown you the trend in sea level, it would also have looked something like this over time. And then chlorophyll. And you can't see it up here, and I'll go to the next one. All of these modes, the time series of all of these modes, are coupled. So you've got SST, sea level, chlorophyll, and sea level pressure are all following each other over time. And then we've plotted the primary productivity anomalies, and they're following the same pattern. So it's this area of variability that's described here by El Nino that's driving most of the variability in primary production. Here's the 97-98 El Nino, the rebound La Nina. So globally, most of the variability is being driven today by these El Nino cycles. If we had a much longer time series, the results might be a little different. But unfortunately, all of our global satellite time series are quite short. I just showed this at the bottom, that terrestrial MPP variability is about the same range that it is in the ocean. We've got about 2 to 2 petagrams, 2 to 2 petagrams. So the variability in terrestrial photosynthesis is about the same as it is in the ocean. What's different is that the terrestrial variability is very tightly coupled to the rate of CO2 in the atmosphere. And I think, someday somebody will do this analysis, I think it's because the surface ocean buffers the fluxes. The CO2 system in the ocean essentially buffers the fluxes. It can't be that, given the same variability, we're not changing the atmosphere. But somebody smarter than I am needs to work through that and show that somehow this variability does propagate into the atmosphere. We just haven't figured out how to propagate that. I say it's a familiar story. I won't go into this very in any detail. These are the El Nino patterns. Colors are temperature. Arrows are anomalies in the winds. These are anomaly fields. El Nino, La Nina. The El Viejo, which is what I have tried to call the Pacific Decadal Oscillation. Most people in the U.S. haven't taken me into account. My friends in Peru and other parts of the world do use it. The patterns are similar, although the impacts seem to be greater at higher latitudes. So we have these multi-decadal oscillations, 3 to 8 years, 40 to 70 years, the periods, and we see these very large changes in the abundances of fish that are occurring over the entire basin associated with these patterns. We now are able to use models, and this is an animation from a ROMS model run by my colleague Yi Chao at JPL that starts in the early 90s and runs to 2007. And you can actually see this change that happens after the 97-98 El Nino, when the ocean on this side becomes much more greener than it was on the ocean over here. And we're starting to use these models to actually try to forecast in some form or another. And when we look at the time series and we compare the models with the observations in the same form, running EOFs of both SST and sea level from the models, we see that these models capture this interannual variability rather well, which gives us hope that, and I think most of this, the reason why they do that well now is because the wind fields that we have available to drive the models are of such high quality. And we can embed ecosystem models into these physical models, and this is a simulation and time series of the first EOF of chlorophyll as simulated by this model, and this is the time series of that. And again, this model now captures this regime shift that we seem to think happened after the 97-98 El Nino, and I've compared it here with the chlorophyll analysis, the chlorophyll anomalies from our time series and the nitrate anomalies from our time series, showing that nitrate at depth or near surface depth has also increased, as I showed you before. And the patterns are similar to those that are found in sea WIFs. So our models are getting better, although we still need a long way to go there. Now we get to the time series of productivity as measured at the time series sites. And this is an interesting conundrum. The main message that I want to give you here is that of all of these records, there's only 2 that are decreasing, and the rest of them are all increasing. Only the two that are decreasing are Cariaco in terms of chlorophyll and productivity. And we think that's due to a shift in the intertropical convergence zone, and I may get to that. What time did we start? Did we start a little late? I'm wondering how long we've... 5 minutes? Okay. I'll have to hurry through this then. Good. Anyway, so most of these time series are all increasing over time, which is very different from the publication that was I referred to earlier, which suggested that productivity is decreasing. But the other interesting feature is that it was very clear, the variability globally was very clear from the satellite data, but it's not that clear from the time series data, except, of course, for the one that we have. I'm not sure if that has anything to do with things, but and again, the variability, as what might be expected from a single point measurement, is much higher than that we can glean from spatially. If we look at some other properties like this one off Hawaii, we do see a shift that we didn't see in the record previous to that. Okay. What I want to do quickly is focus on this oxygen story. And I'm not going to go into the rest of this here today to show just this. We've observed a strong decrease in oxygen associated with this regime shift. And this decrease in oxygen has been happening all along the California coast. And this decrease in oxygen has resulted in the appearance of this giant squid that is here trying to eat our remotely operated vehicle that is about the size of Fizz's car. And these organisms are capable to live under very low oxygen conditions, and they seem to be migrating as this oxygen minimum zone expands in the world. And this is what one of those looks like, and again, they started to show up right after. And if we look at other places in the world, in a place where there is very little oxygen, nitrate is decreasing. And this is a time series of oxygen from Peru, which shows that in the early 60s or 70s, oxygen was lower, it increased, and then decreased again. And I'm not going to go through that part of it, but if we look at California, in a recent paper published by Deutsch et al. In Science, we see the same type of pattern, as if these changes in oxygen are again driven by this multi-decadal variability, perhaps. Although when we look at a little longer scale, it looks like this decrease in oxygen might be a little different than what we've seen before. But who knows? Is this shift that occurred in 2000 a little bit different than what we've seen before? Briefly, during the Little Ice Age off Peru, we took some cores, some of my colleagues took some cores, Gutierrez et al. In biogeosciences, showing that during recent periods there was a lot of evidence of fish and less evidence of fish other than hake in the Little Ice Age. And that seems to be associated with the periods of abundant fish seem to be associated with lower oxygen, higher nutrients, higher productivity, and the periods of lower fish with higher oxygen, lower nutrients, lower productivity, and lower primary production. And again, this is from a paper by Mann. During the medieval warm period, this triangle of anomalies seems to be represented in the paleo record. And that triangle of anomalies seems to disappear during a colder world. So for some reason during the Little Ice Age, the atmospheric circulation patterns were such that the trade winds, at least in the Pacific, and perhaps even in the Atlantic, were modified. So what we think happened during the Little Ice Age is that as the polar ice caps increased, they shifted the ITCC further south, essentially collapsing the southern trade winds. The opposite seems to be happening in a warmer world. So the ITCC seems to be moving northward today, and it's that northward movement that we think is affecting productivity in the Cariaco region. So productivity off of Venezuela is one of the places where productivity is decreasing, but in other places where this triangle exists, productivity may be increasing. And I'm just going to go to the conclusions. Just to say that climate variability has strong and measurable impacts on ocean's ecosystems, and in many ways that variability is not exactly what we expected. The expectation in a warmer world would be for increased stratification throughout the ocean and a less productive world, but maybe not exactly. Ocean ecosystems seem to adapt to this variability, but we don't know what their limits are. We can definitely say global change is occurring, but climate change associated with anthropogenic effects is harder to pinpoint. I argued yesterday in the talk that I gave that I think in 10 years that won't be the case. There's going to be always two faces to things, and there will be many surprises. And I think more recently we're starting to come to this, that our science and management needs to be adaptive. We need to be able to learn and adapt to things as we start to observe the faces of climate variability and change. And I'll stop there and take some questions if you have any.